Jahn Teller theorem. In this case, first of all, you have to know what is Jahn Teller theorem. According to Jahn Teller theorem, any molecule or complex ion in an electronically degenerate state will be unstable relative to a configuration of lower symmetry in which the degeneracy is absent. That is, Jahn Teller theorem states that any nonlinear molecule with a spatially degenerate electronic state will undergo a geometrical distortion that removes that degeneracy. That is, Jahn Teller distortion states for a nonlinear molecule in an electronically degenerate state, so that distortion must occur to lower the symmetry and to remove the degeneracy of the system. The complexes in which the metal ion have unsymmetrical Eg or T2G orbital shows Jahn Teller distortions. One of the important terms in Jahn Teller theory is electronically degenerate state. Then what is an electronically degenerate state? For example, consider the case of D1 configuration with octahedral symmetry. That is, it contains one electron. This one electron can occupy either in the xy orbital, xz orbital or yz orbital. And the energy of these configurations remain the same. That is an electronically degenerate state. That is, D1 configuration represents an electronically degenerate state. Another term is non-degenerate state. Consider the case of D3 configuration in octahedral geometry. That is, 3 electrons can be arranged like this in the xy orbital, xz orbital and yz orbital. Only one type of arrangement is possible in the D3 configuration. That represents a non-degenerate state. In this case, Jahn Teller effect is responsible for the tetragonal distortion of hexa aqua copper 2 complex ion, that is Cu H2O 6 times 2 plus. The configuration of Cu H2O 6 times 2 plus is T2G6 Eg3. That is, Eg orbital is unsymmetrical and hence will show Jahn Teller distortions. In the case of this complex, the two axial CuO distances are 238 pm, whereas the four equatorial CuO distances are approximately 195 pm. From this figure, we understand that Jahn Teller effect is observed as tetragonal elongation and tetragonal compression in octahedral high-spin D4 complexes due to net change in the energy of electrons. Jahn Teller effect does not occur if there is no net change in energy. Consider the first case. In the case of D4 high-spin complexes, in these cases, the Z ligands can move out or can move in. The Eg levels in this case split into two, that is dz square having higher energy than dx square minus y square. That is an Z in case. That is, there is one electron in the dx square minus y square. That is called tetragonal compression. That is, Z ligands can move in. There is a net change in energy also. That is, distortion must take place. And the extra electron is in the dx square minus y square orbital. If the dx square minus y square orbital has the extra electron, we would expect 4 ligands along x and y axis to suffer a repulsion, thus giving a distorted octahedron with 4 long and 2 short bonds. That is the first case. Consider the second case. In this second case, the Eg levels are split into 2, whereas dx square minus y square orbital has higher energy than dz square orbital. That is an Z out case. That is, Z ligands can move out. That is a case of tetragonal elongation. There is also a net change in energy. That is, distortion is taking place in this complex. In this case, the extra electron is in the dz square orbital. The distortion would be in favor of 4 short and 2 long bonds if the extra electron enters the dz square orbital. Consider the cases. In the first case, the extra electron enters the dx square minus y square orbital, and as a result, we get 4 long and 2 short bonds. That is an Z in case. But in the second case, the extra electron enters the dz square orbital. As a result, we get 4 short and 2 long bonds. That is an Z out case. First case is tetragonal compression and the second case is tetragonal elongation. And in the final case, that is a D5 high spin, the Eg level contains 2 electrons. That is, in the dz square 1 electron, dx square minus y square also contains 1 electron. So there is no net energy change. That is, there is no Jahn Teller effect. Due to Jahn Teller distortion, the octahedral shape of the complex may change to tetragonal or even square planar. In the case of empty, half-filled or doubly filled orbitals, there should be no distortion. This figure represents a case of Z elongation and Z compression as in the previous slide. In this case, as a result of Z elongation, we get 2 long and 4 short bonds. And in this case, Z compression occurs. Due to Z compression, we get 2 short and 4 long bonds. Jahn Teller effect is most often encountered in octahedral complexes of transition metals. This phenomenon is very common in 6-coordinate copper-2 complexes. The D9 electronic configuration of this complex ion gives 3 electrons into 2 degenerate Eg orbitals, leading to a doubly degenerate electronic ground state. Such complexes distort along one of the molecular fourfold axis. The molecular fourfold axis is always labeled as Z-axis, which has the effect of removing the orbital and electronic degeneracies and lowering the overall energy. That is, the energy of the system is lowered, degeneracies removed. The distortion normally takes the form of elongating the bonds to the ligands lying along the Z-axis, but occasionally occurs as a shortening of these bonds instead. But Jahn Teller distortion does not predict the direction of distortion. Only the presence of an unstable geometry is detected. When such an elongation occurs, the effect is to lower the electrostatic repulsion between the electron pair on the Lewis basic ligand and any electrons in orbitals with an Z component, thus lowering the energy of the complex. Jahn Teller distortion should occur in the case of uneven filling of Eg or T2G orbitals. But the T2G orbitals will have only a little effect in this case. This is an octahedral complex, and due to Jahn Teller distortion, the complex is changed to tetragonal, and the tetragonal distortion lengthens the bonds along the x-axis. That is, metal ligand bond length should differ. And this figure represents the case of copper-2 complexes undergoing Jahn Teller distortion. That is a case of D9 complexes. Eg level contains 3 electrons. That is, these are unevenly filled. Due to uneven filling in the Eg level, Jahn Teller distortion occurs in this complex. That is, dz square contains 2 electrons and dx square minus y square contain 1 electron. Due to distortion, the bonds in the xy plane becomes shorter. the 2 electrons in the dz square orbital go down in energy. 1 electron in the dx square minus y square orbital goes up. Square planar complexes. Consider the case of 5d orbitals. According to CF theory, the 5d orbitals in an octahedral field splits into two, that is Eg orbitals and T2g orbitals that represent the octahedral structure. When Jahn Teller distortion proceeds, tetragonal distortion is taking place in the complex compound. That is, Eg orbitals are split into two, dx square minus y square and dz square, whereas T2g orbitals are split into dxy, dxz and dyz orbitals, and this one represents the tetragonal structure. When the distortion proceeds sufficiently, then the energy of dx square minus y square orbitals are increased to a much greater extent. And in the case of dz square orbitals, the energy is lowered. In the case of dxy orbital, the energy is raised. And in the case of dxz and dyz orbitals, also energy is lowered. That represent a square planar structure. That is, we obtain a square planar structure when the tetragonal distortion proceeds sufficiently. In the first case, on splitting d orbitals, we get an octahedral structure, and in the second case, due to Jahn Teller distortion, we get tetragonal structure. Due to strong distortion, we get a square planar structure.